to part 3. The reason I want to do part 4 is actually part 5 is linked into what you're doing Thursday in lab. So I figure if we do part 4 today and then part 5 on Wednesday, that'll have things make sense. And that's what I'm after. Inflicting as least pain as possible. So this part is, we're going to be talking more about compounds. And of course, the definition of a compound looks something like this, that a compound is one type of matter that's made up of atoms. But in a compound, we use a formula to represent the number of atoms of each type of element that are part of that repeating unit. So we're diving into compounds now. So compounds can be broken down into their atoms. We're going to look at, again, I think at that mercury 2 oxide where it breaks down into mercury atoms and oxygen atoms. No nuclear chemistry needs to go on in breaking those, what we call the chemical bonds of a compound to make the individual breakdown into individual atoms. Okay? So we use chemical formulas to represent the repeating unit that's either a molecule or a formula unit. This is a video we watched before. We'll take one more look at it. Well, we need to take a closer look at taking compounds and dividing them into the 2 types of compounds. So all matter is made up of atoms, and it has mass and occupies space. Matter can either be a pure substance or a mixture. And if it's a pure substance, it can either be an element or a compound, CPD for compound. And of course, just like we saw a minute ago, we can take a chemical reaction, break the compound down into its elements. We can take some sort of chemical reaction, raise up the elements to form compounds. So this is some sort of chemical CHM165. This is supposed to be my CPD. And then compounds, there's further 2 types of compounds. They are molecular compound and ionic compound. So what I'm going to do, and it works pretty well, is we are going to kind of compare and contrast molecular compounds with ionic compounds. There'll be various things throughout this lecture to put on this in our little tabs. All right. So there's one already in italics. So for instance, molecular compounds, if we have a repeating unit, we're going to call that a molecule. So molecule is equal to a repeating unit. If the compound is an ionic compound, we're going to call that a formula unit. Formula unit is equal to the repeating unit. By the way, no joke, actually, you'll see this on bottles of ionic compounds. Of course, the abbreviation for formula unit is NFU. It really is formula unit. Anyway. Okay. There are definitely some differences between these 2 types of compounds. Another thing to add to our compare and contrast. Now, under the ionic compound column, we can do this. We can say for ionic compounds, I'll put a big M for metal is bonded to, and I'm going to put a dash, 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 to an NM, which stands for nonmetal. Metals bonded to nonmetals. And of course, we talked about how you can find whether something is a metal if it's on that side of the jag and the left of the jag, and we have very few nonmetals. It's kind of in the upper right-hand corner. Those are our nonmetals. So look for the metals. If we compare that to molecular compounds, for molecular compounds, it's amazing. Molecular compounds generally have those little nonmetals bonded to other nonmetals. So over here, I'll put NM for nonmetal. I'm going to actually put a solid dash. I'm going to put another NM for nonmetal. And here I'm going to put no metals. No metals allowed for molecular compounds in general. Now, I don't know if this works for you. This is my first time to do this, but this actually, as I have this solid line and this dotted line, that is my chemical bond. Chemical bond. That's my chemical bond. And those are atoms. Non-metal atom, non-metal atom. Covalent compound, metal atom, non-metal atom. It's going to be an ionic bond. Cool. So I'm going to add one more thing to, I guess it'd be to my molecular compounds. Under my molecular compounds, I'm going to put the element H, so I'll just put the symbol for H. H is a nonmetal. Hydrogen is a nonmetal. So like on the periodic tables that I have all over the place, and you have for your exams and everything, I usually have hydrogen in two places. It's over 1A, and it's also over 7A, just to the left of helium. So we're going to kind of picture hydrogen over there. I'll kind of show you why that is. But so if you're given the formula of a compound, if there is a metal, then it's an ionic compound. So, but I told you hydrogen is a nonmetal. So here we have carbon, and don't be ashamed. Sometimes people are like, how do I know carbon's a metal or not? Well, look at the periodic table, because you probably have one handy. So we're going to find carbon here in our nonmetals, and I told you hydrogen is a nonmetal. So this actually definitely is a molecular compound. We could say the same thing about water. We have the two elements are hydrogen and oxygen. You look at the periodic table, you say, are either one of them a metal? Of course, I said again, hydrogen we're considering a non-metal for purposes of identifying the compound is molecular or ionic. We'll be talking more about this actually probably Friday, maybe Friday or into next week. But these things that look like kind of antenna, of course we have, it's H2O, so we have oxygen, hydrogen, hydrogen. Those are actually electrons. That one pair of lone pair electrons, one pair of lone pair electrons. Ammonia, NH3. So we have the central nitrogen atom, hydrogen, hydrogen, hydrogen. Again, we have one pair of lone pair electrons kind of jutting out of the central nitrogen atom. If we were to identify, or we would identify this again as a all nonmetals. Nitrogen, you clearly see it's part of it's nonmetal, and hydrogen we consider nonmetal. So that's why actually the caption of this slide is that's also a molecular compound. I don't think there's a whole lot to this one. So I have some images of, I like what I saw, the image better than this, because this doesn't show the small cation, the big anion. Okay, but this is the crystalline lattice structure. You can see this better though, if you pick on any, so here they're saying the green are the chlorine anions. Again, so you can go this way, this way, this way, this way, this way, or this way. So 6 different ways. They have a cation and anion, and you have a repeating unit we call a formula. Sodium chloride, just kind of a different look at it. No kidding, I had I think it was an introduction to general chemistry textbook one semester where they had their crystalline lattice structure wrong. They had it like anions connecting them with other anions. So kind of back to the title of this is molecular compounds. Okay, molecular compounds, we use the term molecule to represent or to talk about the repeating unit. And so like this says, if you have a water molecule, you know what 3 atoms are going together to make that water molecule. No doubt about it. If we compare that to sodium chloride in a crystalline lattice structure, you don't really know which anion goes with which cation. It's more of a commune. So here I said for ionic bond, I said electron is transferred. I want to step over here to our molecular compounds where I have a solid line between my two nonmetals. That chemical bond actually is a covalent bond. And molecular compounds are noted by having all covalent bonds. And I'm going to say covalent bond is equal to electrons, E superscript negative, shared. Electrons shared. All right, so far so good. And an ionic bond, which is characteristic of all ionic compounds, have at least one ionic bond. Now, ionic compounds could have a mixture where electrons are shared and electrons are transferred, but at least one set between two atoms, electron has been transferred to make it an ionic compound. So an ionic bond is, and it's kind of a stepwise process. We'll talk about why electrons are transferred. I'll tell you right away that the reason that the metal sodium for instance, wants to give up one electron is if you find sodium on the periodic table, okay, it's actually just one electron past being a rare gas configuration. The rare gas configuration, instead of 11 electrons, of course, would be 10 electrons. So in losing one electron, it becomes a +1 charge, and in losing one electron, its nucleus is the same. It still has 11 protons, but now it only has 10 electrons. And now it has the configuration as with regard to electrons as if it were neon. And that's why it does that. So that's why sodium does that. Chlorine, we said, picks up one electron. And the reason chlorine wants to pick up one electron is it wants to be like argon. So it has the heart of a chlorine atom, but now it has the electrons associated with an argon, which is 18. And they're configured the same way as those 18 electrons on an argon atom would be. So now it's got one extra electron, so it's a -1 charge. So anyway, and so then you have something that's positively charged, something that's negatively charged, and have that electrostatic force that we call an ionic bond. So under ionic compounds, it contains at least one ionic bond. So ionic compounds, at least one. So like I said, you can have an ionic compound that has electrons shared or covalent bonds, but it has to have at least one ionic bond. Now, as I've been talking about these ionic bonds, electrons transferred, or covalent bonds, electrons shared, hopefully you kind of getting a sense for these are what we call the chemical bonds that's connecting the molecule or the formula unit. These aren't what we'll call intermolecular bonds. These are more basic than that. So if we contrast that to molecular compounds, oh, by the way, under molecular compounds, we can put sometimes instead of molecular compounds, you'll see, I'm going to say same as covalent CPDs, covalent compounds. They mean the same thing. So those are synonyms. Sometimes synonyms can be very annoying. But if it's a molecular compound and or a covalent compound, then it must have all chemical bonds are covalent, where electrons are shared. So actually, it's annoying at synonyms. You'll hear me kind of lapse back and forth between covalent and molecular. So. At the crux of, say you have atom A and atom B and you want to put a chemical bond there. The driving force of whether electrons will be transferred or electrons will be shared is what we call the electronegativity of atom A and atom B. The Greek letter, it looks like a fancy X. This is the Greek letter chi. I think it's an uppercase chi, I'm not sure. And that means electronegativity. Oh my goodness. You know what I mean. I think I've totally butchered electronegativity, but that's what it means, electronegativity. And it's a tug of war. Basically, you have atom A, and you know it wants to bond with atom B, but you look at their electronegativity, and if this one's higher, that means the electron cloud is going to go over there. If this one's higher, if A is higher, then the electron cloud is going to go over there. You know you're going to put, I'll go ahead and tell you, I'll just do it this way. You know, they usually come in pairs. You know that you're going to have 2 electrons between those 2 atoms. But who's going to tug on it more? That is indicated by its electronegativity value of that atom A or atom B. Okay, so electronegativity, chi, is the pull that an atom is going to have for electrons in a bonding situation. So the way this works is metals generally have, I don't know if I can do, I don't think this fits over here. But metals tend to have low electronegativity values. So what does that mean? So I'm going to put M for metals, low chi, low electronegativity. If it has low electronegativity, that means it's like, hey, I don't want those electrons. Here, you can have them. And so actually, with the low electronegativity, that's why metals tend to go ahead and give up electrons. We saw that with sodium, didn't we? And nonmetals in general, and we're going to look at some tables with electronegativity or chi values. Nonmetals tend to have high, I love this phrase, high chi, high electronegativity values. Okay? And so in doing that, okay, they actually will say, give me the electron. And so the nonmetals tend to get electrons, become negatively charged. With the low electronegativity values, the metals tend to give up electrons, become positively charged. So that's kind of exactly what we saw. Those are just kind of generalities. In this part, we're going to be looking at the periodic table more of the elements, and we're going to be oftentimes just focusing on the group A elements. The group A are main group elements, those are synonyms. So the group A elements would be these S block and the P block, right? Group A, S block and P block. So we take out the D and the F, we set them aside. So electronegativity will increase across the period from left to right. So electronegativity increases this way. And the way I like to look at it is that electronegativity increases as you go up the group. So we kind of have a meeting of electronegativity. It's like chewing gum and walking at the same time. Okay. So electronegativity has that trend. So here are some looking at electronegativity values. Sometimes, again, another synonym, if you ever have, hear the word Pauling values and electronegativity values mean the same thing. Linus Pauling, I think I'm getting that right, actually earned, I think, a Nobel Prize in chemistry for his work with electronegativities. So you can kind of see where these group B elements, these D block and F block down here, they kind of do their own thing. But in general, if you take hydrogen and put him over there on top of fluorine, like he's a halogen, then it kind of fits. So it increases as you go from left to right, and increases as you go up the group. Electronegativity. This is a picture from OpenStax, your textbook, and you can kind of see now not the bars, but you actually see the value, the chi value, the electronegativity or the Pauling value here. So it increases from left to right and increases up the group. If you ignore the D block and F block. So I'm hoping this, actually for your homework, and I haven't done homework for this part either, but I'll try to do it tonight. I don't know how to scan in. I'll see what I can do. you might need these values for your homework. So, that's your magnifying glass. So for an electron to transfer, we need a high difference. We need a pretty low electronegativity value for your metal, pretty high electronegativity value for your nonmetal, and bada boom, an electron will transfer. You have an ionic chemical bond. If you have two atoms, atom A and atom B, and if you go ahead and look at their electronegativity values, and they're pretty similar, then actually they're not, difference isn't big enough to have an electron transfer. Electron will be shared, and that bond between those two atoms will be covalent. So this alludes to something I want to talk about, electronegativity differences. Now, we talked about temperature differences. We talked about temperature differences. We did delta T, right? If we talk about electronegativity differences, we do delta chi, which, makes me really feel Greek, right? So we can look up a electronegativity value for A, look up an electronegativity value for B. We can come up with the difference, the electronegativity difference. We're going to use the delta sign, Greek letter, delta chi. And actually, we are most interested in the magnitude of the difference. So usually, it's associated with an absolute value. So we just take the absolute value of the difference between A and B. It's like that. Electronegativity difference. Delta chi. I'm going to kind of give you some thresholds. As I was getting ready for today's lecture, I was like, wow, OpenStax, they have different criteria for having it large enough. This is pretty big, electrons going to be transferred. If this is pretty wimpy, electrons are going to be shared. So if you pick, and we're going to look again at some Pauling values of the nonmetals. If you pick two nonmetals and you go ahead and do this math, this is going to be pretty wimpy. So electrons are going to be shared. If you go ahead and pick a nonmetal and a metal, okay, calculate the electronegativity difference, it's going to be really pretty high, the electron will be transferred. So that will give us an ionic compound. So here we go. This is, like I said, this is a little bit different than I was used to, but I believe it. I've been out of that. I believe what OpenStax says here. So the title of this first column is electronegativity difference between two atoms. Electronegativity difference between two atoms, right? If it's 0, guess what? It's covalent, and it's a special situation. We call it a pure covalent bond. The other extreme down here, say you go ahead and calculate a delta chi, electronegativity difference, and the threshold they have here is 1.8. We're going to look at some Pauling or some electronegativity values. And if the magnitude of the difference exceeds 1.8, which I think in my, did I do like 0.7, I think, in the past? I'm kind of talking this here because in my intro, I think I did 0.7, maybe 1.8. Then an electron's going to be transferred. The difference is great enough that it'll go from the low electronegativity value to the high electronegative value. And then we have something in between. So if it's between 0.4, these are the electronegativity differences between, maybe I did 1.7, because 0.7 wouldn't be enough. Must have been 1.7. I think I used to do 1.7 instead of 1.8. If it's between 0.4 and 1.8, okay, actually it hasn't met the 1.8, so electrons are still going to be shared, but they won't be shared equally. And so it's a type of covalent bond, but we call it a polar covalent bond. Electrons are shared, but they're not shared equally. And I'll kind of show you how we handle that. So as you kind of move up and down this continuum, so you have a purely covalent bond between atom A and atom B, where the electronegativity difference is basically 0 or less than 0.4. Okay, all the way up here to electron is transferred above 1.8 is your delta chi. So I'm sure you're going to have homework and so on. that you can analyze the situation between two atoms. So here we have, this could be, well, this is chlorine. Remember, chlorine is one of the Hoffer-Nichols, so it's Cl2. So here are two chlorine atoms that are joined together. If I were to look up the Pauling value for chlorine and subtract it from itself, I would get 0. So that's a case where delta chi is 0. That's a pure covalent bond between those two. HCl, if I were to look up the electronegativity differences between those two atoms, actually electrons are going to be shared there too. But the chlorine is more electronegative than the hydrogen, so that they aren't shared equally. What we usually do then, we'll be doing more of this in Chem 2, is there's my hydrogen, there's my chlorine. This delta chi is not above the 1.8, so electrons are going to be shared. Chlorine is more electronegative though, to show that the lines, well, more electrons are over here even though they're not transferred. What we do is we do a lowercase delta, which looks like an S with a kind of fancy tail on it. That means partially. And we go ahead and say partially negative. And this hydrogen is going to be partially positive. So in other words, an electron isn't entirely transferred to give us an anion and a cation, but it's not shared equally either. So we have, if we were to look at, there's these potentiometric maps, we'd see more electrons over here and less over there. And then we have this one, where, and again, I think we're going to start to look at some numbers. Maybe my slides don't do that this semester. But if we were to go and snag the chi value for sodium, snag the chi value for chlorine, and do this little math here, you're going to see it exceeds 1. All right. So this kind of just recaps a little bit of what I already have over here. If a compound's formula contains both a metal and a nonmetal, then it's probably ionic. So over here, under ionic compounds, I emphasize metal. If a compound's formula contains only nonmetals, okay, then it's probably covalent. Remember, that's synonymous with molecular compound. So yeah, let's see, what did I say? Sodium, now that won't work. These are, hope you recognize the JAG, so these are our nonmetals. So if you take any pair of nonmetals, hopefully you're going to get under that 1.8 threshold. So let's see, what is the highest one we have? I got 4.0. The lowest one we have, 2.1. I got, that's 1.9, isn't it? So that actually is over the 1.8. But usually, if you bond any nonmetal to another nonmetal, it's going to be under the 1.8. I feel like this is a little bit of review too. So when we did the electron configurations, like we've done, this is Monday, last week, we said that the electrons in the highest end are the valence electrons. Okay, that's all this is talking about. But hopefully you remember that we can know how many valence electrons any element has if we find it on the periodic table and we look at the group number. If it's a group A, if it's a main group element. So one of these days I should bring in a black marker and mark this, 1A, 2A, 3A, 4, 5, 6, 7, 8. So for instance, we have 3 valence electrons here, 4, 5, 6, 7. And again, this seems like kind of a review thing. The group 8A elements are the rare gases. And like I said a minute ago, atoms will try to get the same electron configuration as them by either picking off electrons, what metals do, or picking up electrons, what nonmetals do. And in doing this, like we kind of really saw the sodium video, you saw an electron transferred from the sodium to the chlorine. It was positive charge, negative charge, and then we have a dot. I call it a dot, 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 dot. That's when we have an ionic bond. It's not, we'll be talking more about why when electrons are shared, how does that work? But you're going to see actually they get a rare gas configuration as they share electrons. And then there is your so that's as far as I'm going to get. So there's a good chance we're going to just go on and march through part 5 on Wednesday. And come back and pick up atomic size. March.